Hello and welcome. In this video and a couple of other videos in the sequence, we're going to talk about the concept of probabilities. We would not make any assumption about your background. Let's get started. So let's start with the terms experiment, outcomes, and events. Let's understand this with the help of an example. We all know there is a standard unbiased die, which can be rolled, and when we roll a die, that can be considered an experiment. So rolling a die is our experiment. Now, what could be the possible outcomes when we roll a die? One of the 6 faces would show up. So the outcome would be any number between 1 to 6 for a standard die. What would be an event? An event would be a specific collection of outcomes. Let's say we talk about an even number showing up. So this is an event. If you look at this slide, you should get complete clarity that we start with an experiment. Experiment could have multiple possible outcomes. An event would be a collection of some of these outcomes. So the event in our case is an even number showing up, which obviously would be either 2 or 4 or 6. Likewise, can we talk about another event, which is that the number that shows up is divisible by 3. So now you know the event that you're interested in would contain 3 and 6. Likewise, we can say the number should be less than 5. Now we know the outcomes which are suitable for this kind of an event would be 1, 2, 3, and 4. With this understanding, let's move to the basic definition of probability or the classic definition of probability. Probability PA of an event A, which can occur in m favorable ways out of n equally likely outcomes, is given by m divided by n. So what are equally likely outcomes? When the probability of occurrence of each outcome is one and the same. So when we roll a fair die, we don't have a biasness that only an even number would show up or a number less than 5 would show up. Every number stands an equal chance to show up on top, on the face. Those are called equally likely events. So our classic definition of probability states that when we are looking for the probability of an event A, we have to first get the favorable outcomes, the outcomes of interest, and divide it by something that's known as the sample space. We will talk about this more in the subsequent slides. A couple of properties associated with probabilities. The probability would always range between 0 and 1, where 0 means an impossible event and 1 means an event which is certain or 100%. Let's understand the concept of sample space and other associated terms a little better. We'll look at the complement rule first. So our sample space is nothing but the collection of all possible outcomes. An event can be a subset of a sample space, right? So when we roll a die, the sample space would be any number from 1 to 6. When we say an even number showing up, that's an event. So sample space is a collection of all possible outcomes of an experiment. Let's say we are interested in a particular event, which is an event A, which is our outcome of interest. This A would be a subset of the sample space only. It's a smaller collection of the possible outcomes. And complement of A would be the sample space without A. So in this image, you can see that we've tried to remove A completely, and what's left there, all this red shade that you see, is representing the complement of A. Why is this important? A and the complement of A put together would be equal to 1. Or in other words, we can say probability of an event A is equal to 1 minus the probability of A's complement. So this prime kind of a sign here, which we can read as A prime, is representing the complement event. If I bring this PA prime here to the left, you can imagine it will be PA plus PA prime is equal to 1. Now let's move to the addition rule. And we will understand this with the help of a Venn diagram. So let's say we have a sample space, which is this red rectangular space, and we have an event A and event B. As of now, you can see these events are not touching or crossing each other. They are quite separate. A and B both are subsets of the sample space, but they are non-overlapping. Now the next case, you can see that A and B now seem to be overlapping. They have some region or some area which is common between A and B both. This common area is referred to as the intersection. We call it the intersection of A and B. And if we just look at the outline of this entire shape that we got, that is known as the union. So the symbol is an inverted U for intersection and U for union. So if we were to write a formula for the union, it will be written as this. Probability of A union B is equal to probability of A plus the probability of B minus the probability of A intersection B. Let's understand why we are subtracting the probability of A intersection B from the sum of probability of A and probability of B. This overall region here that I'm outlining, this black region is A. This golden region is B. If we add these two together, we will get something like this, but it will be doubly counting this common area. So we are okay to have this area either from A or from B's end as an overlap once, but we don't want to count it twice. So when you look at A union B, it is right now counting it twice. So just to adjust for that, we subtract A intersection B, and then we get this outlined region, this black region, which is known as the probability of A union B. Now imagine if A and B were disjoint events like these, which means they don't have anything in common. Then obviously the A intersection B piece goes to 0. And you can write the addition rule as probability of A union B is equal to probability of A plus probability of B, specifically for disjoint sets or disjoint events. Let's have a few problems with the help of a standard example, which is related to a deck of cards. So we all know a deck of cards would typically contain 52 cards of 4 types. We could be looking at a spade, a heart, a club, or a diamond. Let's try to answer a few questions related to the deck of cards and how does probability play a role here. So let's say somebody asks you a question, what is the probability that a card drawn at random is a spade? Let's try to understand how we can solve this. Our sample space would contain all 52 cards. That's the scope. What are we talking about? We're talking about a particular type of card, which is a spade. And we know in a fair deck of cards, there would be 13 spade cards. So the outcomes of interest are 13. And the sample space is 52. As per the classic definition of probability, if we apply the rule m by n, which is outcomes of interest divided by the sample space, we'll get 13 by 52 or 1 by 4 or 25%. So if you randomly pick up a card from a fair deck of cards, the probability that it's likely to be a spade is 25%. Moving to the next question, what is the probability that the card drawn at random is a spade or a club? So now we are talking about 2 possibilities. It could be a spade or a club. How do we solve this? First of all, this is a case of disjoint events. A card cannot be both spade and club at the same time. So can we find out the probabilities of each of these events? We know that in our deck, there are 13 spades and 13 clubs. So probability that the card is a spade is 13 by 52. Probability that the card is a club is 13 by 52 again, because both have 13 cards as the outcomes of interest, and total possibilities remain 52. Now, when we talk about an OR event is a spade or a club, we normally perform addition. And even if we go by the rule of addition, it is just a simple addition of these 2 probabilities that we computed above. So as you can imagine, this is going to be 26 by 52 or 50%. Because there is no intersection in between. Now let's take another question. What is the probability that the card drawn at random is a spade or a queen? Let's visually look at it. This is not the case of disjoint events. While you could have a card which is a queen, there could also be a queen of spades. So they have some amount of overlap. Can we list down these counts here? So we have 13 spades. We have 4 queens of all the 4 types. But there is something in common, which is a queen of spades, and that count is 1. So in this case, when we calculate the probabilities, we will have to take into account the individual events, which is probability that the card is a spade, 13 by 52, probability that the card is a queen, which is 4 by 52, and probability that it is a queen of spades, it's going to be 1 by 52, just the intersection piece. So now if we have to find the probability of A union B, it'll be probability of A plus probability of B minus the probability of A intersection B, which turns out to be 16 by 52. And we can do the math to find the exact answer. Let's move on to another type of problems, which are popularly known as the problems based on the contingency table. So what is a contingency table? A contingency table is a kind of crosstab using 2 categorical variables and their frequencies in the cells or the counts in the cells. So look at this contingency table, for example. This talks about students from a college who could have studied one of the 3 streams, electronics, mechanical, or computer science as a part of their engineering course. And they could be placed in any of the 3 companies, company A or company B or company C. So how do I read a cell here? First of all, this talks about 22 students who studied electronics and got placed in company A. Any cell within the table would be read like this. For example, this 32 here represents the students from mechanical background who got placed in company C. And then we also have these margins, which are the row totals or the column totals. So if I read this number 68, it means company A hired total 68 students. Likewise, this number here shows that there were total 85 students who studied mechanical. And in total, we have 229 students. So now there could be questions based on this table that we may want to answer. Let's have a look at the first question. Probability that a student chosen at random is a student of computer science. So this is talking about the student coming from a computer science background and chosen at random from the overall data. So outcomes of interest in this case would be the total for the computer science background, which is 69. And then we divide it by 229 to get the answer, which is 69 by 229. Straightforward answer. This is also known as the marginal probability because the value of the numerator and denominator both come from the margins. These are the margins, the row totals and the column totals, right? Let's look at the next question. Probability that a student chosen at random studies mechanical engineering and qualifies for company A. So now we are talking about something to do with the rows as well as columns. We are talking about the student is studying mechanical. So this is the column that we are referring to. But we're also talking about the student qualifying for company A. So in this case, we will be talking about this column and this row. And where do they intersect? They intersect at this point called 28. So the answer in this case would be 28 divided by 229. Some of you are thinking it will be 28 divided by 85 or 28 divided by 68. Just hold on, you'll get more clarity on that when we talk about the conditional probabilities. But there is no condition here. We're just talking about two events occurring together. And we are talking about an intersection kind of possibility here. So student studies mechanical and gets placed in company A. This value would be the outcome of interest, which is 28. There is no restriction on the sample space. We are going to divide by 229 only. So the answer is 28 by 229. Let's move to the next question. Based on the same table, probability that a student chosen at random studies electronics and gets placed in company B or company C. So if the question was just limited to company B or just limited to company C, we would have answered that just like the previous question. But now it says company B or company C. So how do we solve this? First of all, we have to look at the student being of electronics stream and then look at the possible intersections with getting placed in company B or company C. So this will be 34 by 229, which is the student studies electronics and gets placed in company B. And since we are talking about an OR event, we are going to add the other probability, which is going to be a student from electronics background getting placed in company C. Notice this is the same case where student at the same time cannot be placed in both company B and company C. So this is a case of company B and company C being disjoint. And that's why when you're calculating the probability, you are not adjusting for anything in common. You're just adding the two probabilities simply using the addition rule. Let's look at another question. Probability that a student selected at random studies mechanical engineering or qualifies for company A. We are not saying and qualifies for company A. So we have to be very careful with the choice of words in the probability related problems. How do we find this? Student studies mechanical engineering or qualifies for company A. This is actually an intersection kind of a problem because it is a possibility that student studies mechanical engineering and qualifies for company A. So you have to adjust for that event. The probability in this case would be, first of all, studies mechanical engineering, 85 by 229. Then we talk about qualifies for company A. This could be 68 by 229. But then we have something in common as well. Studying mechanical engineering and qualifying for company A. So we have to subtract this 28 by 229 there. The answer would be 85 by 229, which is the probability of the event. We can say the student is from a mechanical background. Then 68 by 229, which is the probability of the event that the student got placed in company A. And then subtracting for the common portion, which is 28 by 229. We'll get our answer, which is 125 by 229. Now let's move to the concept of conditional probabilities. And you can observe the change in the way the problems are stated when it comes to conditional probabilities. There would be conditions indicated very clearly in the language itself. But the basic definition of conditional probability states that conditional probability is the probability of occurrence of event A, given that event B has already occurred. If we say so, it will be represented as probability of A given B. This is how we read it. This is a pipe symbol. We read it as probability of A given B, and it's given by probability of A intersection B divided by probability of B. So let's answer some questions based on this. What is the probability of randomly selecting a student of electronics given that he's been placed in company A? So there is a change now. We are not saying the student belongs to electronics stream and has been placed in company A. We are saying that given that the student has already been placed in company A, What is the probability that he or she was a student of electronics? And in order to answer this, let's look at the same contingency table. So if we state our events like this, that probability of A is selecting a student of electronics, and probability of B is getting placed in company A, then probability of A given B is written as probability of A intersection B divided by probability of B. So what is the intersection between electronics and company A? 22 by 229 is the intersection. Why? Because these are the students of electronics who got placed in company A. And then what is the probability that student gets placed in company A? This will be 68 divided by 229. If we take a ratio of these two, we'll get the answer, which is 22 by 68. But just to give you a simpler trick to solve such problems, when it is known that the student has been placed in company A, you may reduce the sample space to 68 because we are no longer supposed to look at 229 students. We may just look at 68 students who've been placed in company A because that's a given. And within that, how many students were from the electronics background? That was 22. So you can straight away get the answer, which will be 22 by 68, or you can apply the formula and you'll get the same answer. The probability turns out to be 32.3%. Let's move to another concept, which is the idea of dependent and independent events. So first of all, two events A and B are said to be independent of each other if the occurrence of A has no influence on the occurrence of B and vice versa. So neither A affects B nor B affects A. Occurrence or non-occurrence of one doesn't affect the occurrence or non-occurrence of the other event. In such cases, the probability of A given B would be probability of A because B has occurred or not occurred does not influence A. Likewise, probability of B given A would be same as probability of B because if A has occurred or not does not have any influence on B. But if this does not hold good, then we say that the events are dependent events. Let's try to validate a few events here, whether they are independent or dependent using the same contingency table. So let's say the first event is selecting a student from electronics background, and the second event is getting placed in company A. So we calculated some time back, the conditional probability of this was 32.3%. Probability of A given B. Is this the same as probability of A? Probability of A is selecting a student of electronics. So what is the probability of selecting a student of electronics? 75 by 229, which is 32.7. They're not the same. A given B is 32.3 and A is 32.7. We don't do approximations here. These are not the same. So when the probability of A given B is not the same as probability of A, we would say that the events A and B are dependent events. Now let's talk about the multiplication rule. We already saw something known as the addition rule where we use the property of disjoint events. But multiplication rule requires us to use some properties of conditional probability. From the conditional probability equation, we know that probability of A given B is probability of A intersection B divided by the probability of B. So we have just rearranged the expression of conditional probabilities to write it in this form. If we divide the left-hand side with probability of B, it will be the same as the formula of probability of A given B. And from the property of independence of events, we understand that probability of A given B is the probability of A. So now if I put this A in place of A given B, what we'll get, probability of A intersection B is nothing but probability of A into probability of B. This is known as the multiplication rule. So when the events are independent, we can say that A intersection B can be written as the product of the probabilities of the two events. So let's look at a simple example to understand the independence of events a little better. So let's say we are talking about 5 tennis balls. 3 of them are red and 2 of them are black. At this stage, what is the probability of picking up a red ball? Or what is the probability of picking up a black ball? We can easily write that. Probability of picking up a red ball would be 3 by 5. Total choices are 5 and there are 3 reds. Similarly, the probability of picking up a black ball would be 2 by 5 because the total choices are 5 and there are only 2 black balls. So let's say in the first tile, we picked up a black ball. Now what we are left with is this collection. Now if somebody asks you, what is the probability of picking up a red ball? You would say that will be 3 by 4. And probability of picking up a black ball, you'd say it will be 1 by 4. Why? Because total possibilities are 4. We have only 4 tennis balls left now. And reds are 3, so 3 by 4. Black is just 1, so that will be 1 by 4. But it is not necessary that we would have picked up this black ball here first. We could have picked up a red ball from here in the first round. And if somebody asks you now what is the probability of picking up a red ball, you will say that will be 2 by 4. And what is the probability of picking up a black ball? You'll again say that will be 2 by 4. Why? Because now you're left with 2 choices of each color. So if you see in this experiment, the trial 2 is dependent on the choices made in trial 1. Why? Because the probabilities are changing accordingly. If in the first trial, we would have selected a black ball, the probabilities look a little different. If we would have selected a red ball, the probabilities look different. So there is a dependence that has been introduced. Let's try to solve a problem with the help of this. Now, important thing about probabilities is that they open your mind to think about possible scenarios. Now, if somebody asks you, what is the probability of drawing a red ball in the second trial? And if you only decide basis this much visibility, only look at one side of trial 2, that would not be the complete answer. You can get the red ball in the second trial in 2 ways. That you first draw a black ball and then draw a red ball, or you first draw a red ball and then draw another red ball in the second trial. So first trial is a black tennis ball, first trial is a red tennis ball, both the possibilities. Then in the second trial, in both the cases, we are saying we are drawing a red ball. If you've understood the scenario so far, you just have to plug those values. So probability of drawing a black ball in the first trial is 2 by 5, multiplied by probability of drawing a red ball in the second trial. When you've done this, it is going to be 3 by 4. And if you would have drawn a red ball in the first trial, the probability of that would have been 3 by 5 multiplied by 2 by 4. Now, why are we multiplying 2 by 5 and 3 by 4? Because both the events together would complete the selection of a red ball. It's an and kind of an event. And why are we putting a plus sign here? Because this is an or kind of a possibility. Either you do it this way or you do it this way. So generally in probabilities, the and events are multiplied and the or events are added. And that leads us to the answer, which is 60%. Couple of important points to understand. When the events are declared as disjoint or mutually exclusive, it does not mean the same thing as independent. In case of disjoint events, probability of A intersection B is equal to 0. You can imagine that Venn diagram I showed you earlier, where there were 2 circles in a sample space and they were not touching or overlapping. So there's nothing in common between them. That's why we are saying A intersection B is 0. But in case of independent events, we saw in the multiplication rule, probability of A intersection B is equal to the probability of A multiplied by the probability of B. Also, when we say the events are disjoint, we mean that they cannot occur at the same time. But when we say that the events are independent, we mean the occurrence or non-occurrence of one does not affect the occurrence or non-occurrence of the other. So not to get confused between mutually exclusive and independent. They are 2 different properties. So we covered a lot of important concepts, fundamentals of probabilities here, and you will see us building more on the probabilities as we progress our journey towards the Bayes theorem and conditional probability to an advanced level. Do watch these videos completely to get the maximum benefit out of it. Thank you.